So, as usual, I'll start with a review of what we did in the previous class, and you remember some part of it, I'm sure. So we are looking essentially at surface flows, and these are flows which happen on the surface. So it's a thin layer flowing on a surface, and it's flowing on top of a heap of the same material. So really here we are looking at macroscopic balances which are depth averaged and averaged across the width. And these help us to understand how the flow happens. And the key aspect of surface flows is that material can deposit on the interface, or the interface can erode, and as a result the heap shape can change. So here are the equations. When we averaged and so forth, we got the continuity equation became like this. Delta is the thickness of the flowing layer, u is the mean velocity in the x direction, and we have averaged in the y and z directions, so that variable will not come. And so this left hand side is equal to minus of gamma, where gamma is the rate of deposition, and if we write it in terms of the velocity, it is the velocity in the y direction, but negative sign, that means it's going downward, evaluated at the interface. So gamma is the rate of deposition. So if gamma is positive, that means particles are being deposited on the heap. And if you look at the momentum balance equation, then you get something like this. These terms correspond to the acceleration of the material, and this term is essentially the net driving force. So this is the driving force due to gravity, this is the resistance due to the bed friction, and this is the resistance due to the wall friction. So we have essentially this. And then of course there is a continuity of stress at the interface, that is between the flowing layer and the fixed bed. And when we equate the stresses, then we'll get a relationship between μm and μs, where μm is μs plus a term that relates to the collisional stresses, that is C's. So if you look at these model equations, then the unknowns, the parameters of the model are μm, μw, μs, and C. So these are parameters, you have to supply those parameters if you want to use this model. Everything else are variables which can be found out. Now we simplified these equations. We said that supposing shear rate is constant, that is supposing gamma dot is a constant, then we can substitute for u using this formula, and this is what the continuity equation becomes, and this is what the momentum balance equation becomes. So wherever there is u, we have put gamma dot delta by 2. So this is how it simplifies. So there's no u in either equation, but you can see now that this term is exactly equal to this. So we can substitute over here and then simplify, and if we do that, then we'll get gamma is just equal to this term. And now if we put cos terms to be almost equal to 1, cos beta m, cos beta to be almost equal to 1, and if we approximate sine of beta minus beta m as just beta minus beta m, and then you'll get this. Here we have taken the minus sign in, so you get beta m minus beta plus mu w into this. So if you look at this equation, this looks exactly like the BRDG model, which we had discussed right at the beginning of the surface flows. So, these are equations essentially give us a deposition rate gamma, which is the same as the BRDG model. Of course, one small difference is this, you get the frictional term, wall friction term also. But if there is no wall friction, then the two models are exactly the same. Only thing, now we know what is the prefactor. It is acceleration due to gravity divided by the velocity gradient or shear rate. But we need to do a little bit more. In addition to the mass balance or the continuity equation and the momentum balance equation, we also need to have some equations which will tell us that supposing you have this interface, and if let's say things are depositing, then obviously the height will change. It will increase if there's depositing over here. So you'll have a term dH by dt, which depends on the deposition rate. So you get dH by dt just gamma times cos of beta, where beta is the angle of the interface. And then we have other geometric parameters. I had made a mistake in the previous, when I talked in the last class. So you have dH by dx is equal to minus sine beta, which was what I put down. And then I put dH by dy, but actually what it should be is dW by dx should be cos beta. So now when we look at all the variables, we have u, delta, beta, gamma, h and w as 6 variables. And you have 3 equations here, and then you have 1, 2 and 3 equations here. So you have 6 equations and 6 unknowns. So you have sufficient number of equations to completely solve any such surface flow problem if you are given the parameters of the problem, which are as we mentioned, the parameters of the problem are mu m, mu w, c and mu s. So 4 constants if we are given, we can solve any equation. And then after that we looked at one simple example where we had essentially a heap and a steady flow on the heap. Of course, we are looking at it from the side. The actual system is actually there are 2 plates like this, and the flow is happening in between those plates. And this separation is B. And we are looking from here. So what we see is a layer of constant thickness flowing at a constant velocity. So what we assume is that all derivatives with respect to time and distance are 0 for this problem. So material comes in from here, flows on top of the heap and then flows out. So just to say that, let's say this coming in at a mass flow rate of m dot, and the same mass flow rate is going out from there. So for this problem, if you look at the continuity equation and put del t by del by del t and del by del x equal to 0, then the entire left hand side is 0 and you will get gamma is equal to 0. So there is no deposition as expected, because obviously at steady state the interface will remain where it is. And then again, for the momentum balance equation, the left hand side is equal to 0, so you just get this. And this, if we simplify, you get, again as we had done before, you simply get this term. And if you again, if you put these terms close to 1, then you'll get beta is equal to beta m plus a term which depends on wall friction. And then if you do an overall mass balance, then here your mass flow rate, which is the input mass flow rate, is equal to the mass flow rate in the layer, which is the bulk density into the mean velocity into the cross-sectional area. Further, you know that the mean velocity is related to the shear rate like this. So if we combine these two, then we can get an expression for delta, which is just given by this expression. And so it goes as delta is mass flow rate raised to the power of half, if gamma dot is almost constant. And so this essentially gives us delta. And so what it says is that as mass flow rate increases, delta also increases. So what this equation tells us is that with increase in mass flow rate, you'll have a higher layer thickness, and as a result, the angle of the heap will also become higher and higher as you go on increasing the mass flow rate. However, if you have zero wall friction, then this term is zero, and then you will just get that the surface angle is just equal to uh, the neutral angle, which is beta m. Okay, so this is what we had done last time. And today what I want to do is I want to continue on the examples, and we'll look at the same heap flow problem, but now for a closed system. That is, I'll have a wall over here, so then the particles can't go out. You're feeding it in, but they can't go out. So then what will happen is that this surface will just go on. So we are in some sense filling a rectangular bin. And so what will be the flow on the surface for that bin? So that we can study. And then after that, we look at a very important problem, which is what is the flow in a rotating cylinder, which is partly filled with a okay. So please stop me if you have any questions. If not, then we'll go on to the lecture itself. Okay. So this is what we were doing last time. And I mentioned what is the problem that we are going to solve today. And so let's start off on a clean slate. (14, 10, 21). Lecture 31. Okay. So what we want to look at is an example. Flow on the, we'll copy this one. Heap with frictional side walls, and we are looking at a closed system. So this is what our system looks like. So this is our container. These are the walls of the container. Okay. And we have a way of pouring material here at a constant rate m dot, as in the previous case. And what will happen is that as we keep on pouring, the material will fill up and we will have a heap like this. So the material will fall like this over here, and then it will flow to the other side. And as it flows, it will create a flowing layer. So there will be a flowing layer here. So this is the layer that is flowing, and let's say this angle here is beta, the angle of the interface, and this thickness is delta, and this mean velocity in the layer is u. So we would like to essentially get a solution to this problem, so which is just slightly more complicated than what we did before. And of course, over here, this part is the fixed bed. So let's make a few assumptions, and as this assumption I mentioned in the last class also. One is that we'll assume a quasi steady state. What does this mean? That though we know that things are changing with time, but we are going to neglect all derivatives. Okay, so we assume that this rate of change for almost all the variables is almost zero, except for one variable, that is age. So we'll just take dh by dt is not equal to 0. Otherwise, all other time, sorry, this is not correct. We are not taking del x by del t. It is quasi steady state. So this means that only del by del t of any variable is equal to 0, except del h by del t. Only that is not 0. Otherwise, all other derivatives are 0. So if we assume this, then what we will get is that del, and another assumption that we'll also make is that mu w is equal to 0. This is just to make things a little simpler and we can integrate everything easily. If that mu w is there, then things become a little bit more complicated. So we can do it, but let's look at the simplest problem first. So if we put in the continuity equation, we have written this many times, but we can go back and see this continuity equation here. So here is our continuity equation, and now only the time derivative we are putting equal to 0. So this is 0, so we'll get this is equal to this. So this is what you get, del by del x of u into delta is equal to minus gamma. So this is our continuity equation. Now at steady, since we have a steady state, or a quasi steady state, this implies that gamma is a constant. And this is constant with respect to both time and x. And the reason is simple, that if, let's say, gamma is varying with x, then the angle beta will change, and then the system will become time dependent. So since we are saying that everything is independent of time, we must have this to be a absolute constant. And so if the length of the layer is L, then this constant we can relate to the mass flow rate as just mass flow rate divided by rho B into L into B, where L is the length of the layer. So what this means is that if in some unit time there is m dot, let's say the amount of material deposited is m dot delta t, then that amount is equal to the velocity that is deposited in the y direction. You remember gamma is just minus Vy at 0. So that's the velocity into the area. The area is L times B. So you have a constant velocity being deposited. So Vy is constant. So you get gamma into LB, that is the volumetric flow rate into density. So whatever is deposited is exactly equal to the input mass flow rate, what is shown here. So this mass flow rate coming in will be uniformly deposited everywhere on this interface, and as a result this will simply go up and the angle will not change. So if this is constant, then we have a really simple equation to integrate, and we will just get u into delta is equal to minus gamma x plus constant. Now u into delta, you can think of that as a flux. That's a velocity into the height. So that is the volumetric flux per unit width in the z direction. So this is what it is. And the boundary condition we have to use is that u delta is equal to 0 at x equal to L. So when you hit the end of the, when you hit this end of the layer, the flux should be equal to 0. So if that is the case, then what we get is the constant C is just equal to gamma times L. So we finally get that u delta is equal to gamma, that is the rate of deposition, into L minus x. So this is nothing very great. It's saying that whatever is the change in the flux is entirely due to the rate at which the material is being deposited on the surface. And this is something that we can even get from just simple physical arguments. Units are correct. This is velocity into distance. Gamma also has units of velocity times the distance. So this is what is the mass balance or continuity equation. This is what it will give us. Now we can use a definition of u, which is just gamma dot delta by 2. And if we put it in there, then we immediately get delta squared is equal to 2 times gamma divided by gamma dot into L minus x. And so then we finally get how our layer thickness will vary with x. It is just going to be 2 gamma by gamma dot into L minus x, this whole thing squared. So this is our second equation, second result, and this is something that we can easily test by doing experiments. And I will show you experimental results in the next lecture. But just now we'll only concentrate on the theoretical part. Then finally we can write down the momentum balance equation, again with del by del t terms equal to 0. Let me go back in our lectures and we'll see what does the momentum equation look like. Well, here is our momentum balance equation, and if we sort of cut out this term, then what we will get is that 4 by 3 del by del x of u squared delta is just equal to writing down from the earlier thing, g delta sine of beta minus beta m divided by cos of beta m. And then if we want to include friction also, then this would be just mu w into g delta squared cos of beta divided by b. So this is what our equation looks like. And again, this is an easy equation to integrate because you know delta as a function of x, and if we sort of neglect how beta varies with x, then this equation can be easily integrated. But instead of that, what I'll say is, let's say if gamma dot is approximately constant, then we can write down, we can eliminate u as before, what we had done before, and then we write u is equal to just gamma dot delta by 2. Then here we will, and if we substitute here, you'll get 4 3 d by dx of, substituting for this, I will get gamma dot squared delta cubed by 4 is equal to g delta sine of beta minus and now if we take the derivative of this, since gamma dot is nearly constant, we take the derivative only of this. So, first of all, this 4 of course cancels out. And then when we take the derivative, we will get 1/3, and this is gamma dot squared is a constant, and then you'll have 3 delta squared into d delta by dx is equal to g delta sine of beta minus beta m divided by cos of beta m by b. Okay. So again, here also the 3 cancels out, and so we are left with gamma dot, sorry, let's write only with blue, gamma dot squared delta squared, and then I divide by g delta d delta by dx is just equal to sine of beta minus beta m divided by cos of beta m minus mu w, sorry, minus mu w into delta by b cos beta. This is the simplified thing. And now we can substitute for d delta by dx. We know what that is. So
Sir,
yeah,
here W is assumed to be 0, not friction.
I know. I thought I'd let's just I'm going to sort of leave it in there. Maybe I'm going to just remove this assumption for the time being, because instead of taking mu w to be 0 and then integrating everything with respect to x, what I'm doing here is I'm taking gamma dot to be almost constant. So that simplification I'm using. So let me change that a little bit. Instead of taking mu w 0, I'm taking gamma dot approximately constant. Sorry.
Okay, sir.
So then now we can look back at this and see, we know what is d delta by dx. Since we are given over here, well, if we simplify this out a little bit, as we had done in all the other cases, we'll put, let's say, cos beta is approximately 1. So that will simplify some things. And then we put sine of beta minus beta m is approximately equal to beta minus beta m. So then what you will get is, and then, if we simplify things out a little bit, then you will get gamma dot squared delta by g into d delta by dx is just equal to beta minus beta m minus mu w into delta by b. And so this gives us an expression for the angle beta is equal to beta m plus mu w into delta by b plus gamma dot squared by g into half d by dx of delta squared. So I put d delta by dx to be equal to half of d by dx of delta squared. And delta squared, we know that's a very easy expression. So this can be written as, I'll just write down this, d by dx of delta squared. If we now look at this expression here, then this is just 2 gamma by gamma dot into L minus x. Okay. So this simply becomes minus two gamma by gamma dot. So this is what and now if we substitute this back in there, then you will simply get beta is equal to beta m plus mu W delta by B minus, since this layer thickness is obviously reducing with distance, so obviously you'll get a minus term here. And then this is, when I substitute for this, 2 cancels out, gamma dot cancels out. So you will just get gamma dot gamma by G. So this is the result that we have. That by doing all this, we have got 2 results. One which we can check easily, that is the delta is just equal to this, and the second one is beta is equal to this. So how does the layer thickness change with distance? We see delta, how it changes with distance. So this will tell us how the layer thickness changes with distance, and this tells us how the layer thickness changes. I'm sorry, this tells us how the angle changes with the thickness, interface angle, and this tells us how the layer thickness changes with distance. So these are the 2 results that we have got, and what we can do now is we can, and I'm not going to do it in this class, but in the next class I'll show you some results which will tell us about I'll just show you some experimental measurements which will show that this model is it works. Okay. Then the next problem that I want to look at is this flow in a rotating cylinder. But before we just think of that, before solving the example, I want to just tell you a little bit about what is known about this flow in the rotating cylinder. So first of all, let's look at the applications. So you in this, what the system looks something like this. That you have a horizontal cylinder or nearly horizontal cylinder, and it sort of rotates about its axis, which is shown here. So there is, let's say, rotating with an angular velocity omega, and it is partially filled with granular material. With particles. Okay, so this is what the system looks like, and there are a large number of applications, and it's used in huge, very large number of applications in many different industries. So, for example, there could be what are known as drum mixers. So you want to blend 2 different powders together, you can put them in there and rotate that. Then there are dryers, rotary dryers. Again, same thing. And then this is also a very large application, which is rotary kilns. In this, there's usually a reaction that takes place in the solid state. So very high temperatures, and the particles are exposed to the high temperature, and then they change their chemical composition. Example of this is a cement rotary kiln and so forth. So many examples of this. And another problem that, I mean, another application that is very commonly used is for coating. For example, tablet coating. It's also done in this type of rotating cylinder. They call them pan coaters. But you know, whenever you get a tablet, you'll see that it's colored by some nice orange or bright red or something like this tablet. And that if you taste the coating, it will be usually sweet or something like that. So that is done to essentially seal the drug inside and to give a protective coating. But the way it's done is that you take those tablets, put them in there, and then there is a spray that is put on the surface. There'll be a spray that is put on the surface tablets, and then because it's rotating, then slowly they get mixed and everything. And so there are many applications of rotating cylinders, and so many people have studied these a lot. There are also many regimes of flow, as you might expect. And the main control parameter, I mean, there are two control parameters. What is the amount of material you fill? That is the fill fraction. And the other one is the rotational speed. So what people have found is that there are, if you are at very low speeds, you get what is known as the avalanching regime. In this regime, what happens is that, you know, you start, let's say, at a certain angle, and very slowly this cylinder is rotating. So this whole thing rotates as a fixed bed until it reaches the maximum angle. So it's just turning along with the cylinder as a fixed bed. And then there is an avalanche, and this entire the material over here, they just gets, I should draw it a little better. Okay. So whatever is the material in this triangle here gets mapped back over there. So you know, it sort of relaxes back to this. So there is just bed, as a solid body along with the cylinder. So it's going very slowly. So it just rotates along with the cylinder until a maximum angle. Then there is an avalanche. Which reduces the angle to the static angle of repose. So then there are these two angles, let's say theta I'm using beta over here, no? Beta S and beta M. So these are the two different angles of the surface, and there is the flow is what you might call an intermittent flow. So, there's no flow, and then suddenly there's an avalanche and it goes back to its original. So this is what it is. So at low speeds you have got this. Then at intermediate speeds you have what is known as a rolling regime, and here you have a nice continuous flow. So you have this is rotating continuously with omega. Here also it's rotating, and you will get a flowing layer on the surface, and over here this is a fixed bed which is flowing. So this is how it's related to. This is of course a rotating fixed bed. So the particles are all fixed relative to each other, but they turn, and this is a flowing layer. Okay. So in this rolling regime, you have a continuous flow, continuous and steady flow, and then you have a flowing layer on a rotating fixed bed. And this is the one that we will be studying in more detail, because this is now again comes under the category of surface flow. And then the third thing is that if you go to high speeds, now what are these actual speeds at which the transition takes place? There's data available for that, and we can look it up. That depends a lot on what is the nature of the material, what is the amount of filling, and the rotational speed. So for each of these things, you will get a critical rotational speed where things will transition from one to the other. But here, I'll just simply mention that there are these regimes, and you will get regime maps in the literature, which you can go and look up. So in the cataracting regime, you have again, so this is higher speed than the rolling regime, and here not only do you have a flow, a continuous flow, but particles are also thrown up and flow. So there is so let me just say that there is continuous flow, but what you have is particles are thrown up due to inertial effects. Okay, so now the thing is rotating so fast that the particles have some momentum, as they are moving with the cylinder, they have some momentum. And so then they don't want to quickly change direction and stick to the flowing layer. They get thrown into the air and then they fly out and go there. And then there is something called the limit and that is the centrifugal regime. Might draw it again and you can just paste it. In this regime, the rotational speed is so high that all the particles are just thrown to the walls of the cylinder. So, I mean, this is why it's called limiting speed, because this is a pretty useless sort of regime. So you don't want to. So they are all along the cylinder surface. And here you can easily find out what will be the rotational speed for this. So, typically if you just say that the cylinder radius is r, then the centrifugal force so the centrifugal force on the particle can someone tell me what will be the expression? I'm telling you that omega is the rotational speed of the particle and the cylinder radius is r. So what will be the centrifugal force? And let's say the mass of the particle is m. So what will be the centrifugal force? Can someone say quickly? Does anyone know what will be the centrifugal force on a particle?
M R omega square.
Correct. So this is going to be the centrifugal force, and the gravitational force is just Fg, which is equal to mg. So, if the particle is over here, that experiences the maximum gravitational force. And so what you expect is that if these two forces are balanced, then the particle will not be able to, or if this force, centrifugal force, is larger than the gravitational force, then the particle will never fall down. So, the critical rotational speed is when these two are equal. So then you will have at the critical rotational speed, you have Fg is equal to F centrifugal, or m omega squared r is just equal to mg, or you can say that omega squared r by g is equal to 1. This term, omega squared r by g, is generally referred to as the Froude number. And if it's equal to 1, then you will be in the centrifuging regime. The Froude numbers we will operate at are going to be much, much less than 1. And many of the people, they will say what is the transition occurs between these different regimes in terms of the Froude number. Much less than 1 means it will be something like 10 raised to power minus 3 or something like this. And this is equal to 1 for the centrifugal regime. Okay. So in the next class, we'll try and analyze this particular flow situation. So we will basically look at what happens in this flowing layer and how we can model this flow in terms of the surface flow equations that we have developed. Okay, so that will be the next example that we'll look at, which is the flow in the layer in a rotating cylinder operating under the rolling regime. Okay. Okay, so I'm sure all of you must be celebrating. So have a nice time tomorrow and over the weekend. However, I will schedule a quiz and I will post this on Moodle, which lectures, to again take up one more topic which you can revise, and it will be the same type of test on next Thursday. Okay. Thank you, and now I'll see you on Monday morning.
Thank you, sir.
Thank you.
Thank you. Bye-bye.